Hello everyone, welcome back to Physical Geology 1403. This is lecture 7, Metamorphism. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. That's everyone. Would you grab the door for me, please? Thank you. Okay. Before we start, are there any questions? Or interesting stories / anecdotes? No? Did everyone at least have a good weekend? Yes, sir. Yes? Did anyone have a bad weekend? Besides Autumn. I already talked to Autumn about her weekend. Huh? You almost fell off a roof, but you didn't, so that's a good weekend. So you did fall off the roof. I fell off the roof, but I didn't hit the ground. You simply didn't land on the ground. You landed in a tree. Okay, so you had a good weekend because you fell off a roof, but you were lucky. Yeah. What kind of tree was it? And how high was the roof? Did the tree break? Did the tree break? It was a two-story house. A two-story house, and you fell into a reasonably sized tree? Yeah. Wow. My grandma's tree hurt. Is the tree okay? Wow. Is the tree okay? I bet it did. Yeah. I have fallen off of roofs and I have fallen out of trees, but I've never fallen off of a roof and into a tree. Yeah. All right. Anything else? Any other interesting stories to share? No? Alrighty then. Last time we talked about sedimentary rocks. So in our rock cycle, we have gone all the way from magma through cooling and crystallization to igneous rock. From there, through weathering and erosion into sediments and therefore sedimentary rock. And now we're continuing our evolution through the rock cycle. Okay? Remind me what diagenesis is.
It's what happens after the transportation part.
Deposition is what happens after transportation ends. Diagenesis is what? There's a definition that I gave you. Reese's Pieces, nice choice. Okay? Diagenesis, the definition of diagenesis is what? Huh? No, it's a process. Well, it's not a process. It's a category, let's call it. I feel like my hair is kind of crazy today. I haven't looked in a mirror. Is my hair pretty crazy? No? Are you sure? It's Albert Einstein. Not crazy at all. Okay. Huh? It's a part of the rock cycle. Diagenesis, I'll give you the start and someone finish it for me. Diagenesis is everything that occurs to a sediment after what? Deposition, but before metamorphism. There it is. That's the definition of diagenesis. Everything that happens to a sediment after deposition, but before metamorphism. That includes the process of lithification, becoming a rock. You remember that? I know, it was so 5 days ago. We've forgotten it already, but that's why you take notes, right? So you can remember this one is important, like on an exam, or when you need to participate in class, right? Yeah?
Are we going to be able to use our notes for the exam?
Are
we going to be able to use our notes?
Yes, you can use your notes for the exam. Absolutely. I encourage you to. When is the exam? My friends. This is the last lecture before the exam. Yeah, so if you've been following the module format in Blackboard, you'll notice that exam 1 covers lectures 1 through 7. And this is, in fact, lecture 7. Okay? Right there, see? Okay, so today is lecture 7. Next time we meet on Thursday is your exam 1 review. So please, this is something I usually say at the end of this lecture, but I'll just say it now while you're all sharp and paying attention and listening and my online students haven't zoned out yet. please come prepared with questions next week. Okay? I do not have like a template or a format or anything for exam reviews. Exam reviews are all about helping you get prepared for the exam, and the best person that can determine if you are prepared is you. What's exam one going to be over? Everything we've talked about so far. So I highly recommend that you go through your notes, see where they are light, where they need a little more love, and come prepared with questions about those subjects. Okay? That's what should guide our exam review. And for my online students, hopefully you're watching this within the next 2 days before that exam review. Send me an email with your questions, and I will address those questions in the exam review video, which you should watch before taking the exam. Okay? If you're not watching my exam or my lecture videos within a day or two of me posting them, then you've got big problems, okay? Because we have an 8-week semester, and you can't be that far behind. All right? Right after I close the exam review on Thursday, the exam will open. And then you will have 24 hours to take it. Okay? Well, yeah. For now, let's stick with that. That's the plan we'll stick with for now. That's my usual format. I might adjust it depending on what happens between now and then and how our exam review goes. But for now, let's just stick with that plan. Good question. Any other questions, by the way? Great. And yes, your notes are the one resource that I allow you to use. No textbook, no AI. And yes, I have ways of figuring it out. All right? So, where was I? Metamorphism. Right, diagenesis, anything that happens after the deposition of a sediment, but before metamorphism. So last time we talked about everything before metamorphism. Now we're talking about everything starting with metamorphism, okay? Let's start with a good old observation exercise. Describe what you see on the screen to me. Fossils. What do you mean by fossils? Are minerals fossils? No. Okay, so you're changing your answer. Okay. So you're saying that you're seeing different minerals. It's a pretty wide view. I mean, absolutely, what we're seeing here are minerals, but you can't really tell individual minerals by looking at that, right? This is a pretty high up view.
It looks like it was all weathered, like coming down or something.
Okay. So you're pointing out that it looks like it may have been weathered a certain way? How so?
It's just like all the lines go this way, like in the rocks, like
Ooh, and what do we call those lines, my friends?
layers.
There was another term that we learned. I'll give you a hint. You were all sleeping in them until a few hours ago. Yeah, those are beds. What you're looking at are bedding planes. You remember that terminology? Right, bedding planes, where you can see a distinction between layers of similar rock. Something changed, grain size, cementing quality, something about it has changed to the point where there are distinctions between those individual layers or beds. Okay? But what are they doing? What are these beds doing? Building up. To what? I'm not saying that's right. I'm just asking you to elaborate. Remember, in science, we describe as best we can. I'm not asking you to give me technical jargon about this. Describe it in the words that you know, and we'll dive into it. Yeah. Oh, yeah, sure. Yeah.
The sediments look like they're like slanted kind of.
The sediments or beds? Remember, the sediments are the little grains. beds are the layers of rock that you are looking at.
The beds, they look like they're like, because if you look at like, the right side, you can see how like, it like follows the same line, the beds are following the same line throughout the, yeah, like that.
So you're pointing out how these beds are kind of going off in that direction?
Yes.
And then what?
And then,
Good observation. These beds are most certainly going off this way, but then what do they do?
Curve.
Yeah, they curve around and come back down this way, don't they? What a weird thing we're looking at here. All these layers, all these beds curving around inside of this rock. What could cause that? What?
water.
Huh? Water can weather and erode, but it can't take a flat layer of rock and do this to it.
Mud.
Huh?
Mud.
Mud? How is mud going to do that? Mud is just dirt with water in it. Remember, the rock is already formed. We're not talking about sediment anymore. We're talking about hard rock, layer upon layer upon layer. But what has happened to them since they have become rock?
If more rock builds up along the sides and like pushes it down.
Okay, now we're thinking scientifically. You're thinking about forces that could cause this to happen. I'm looking for a little more generalism than that, though. You're proposing a scenario. We're not to scenarios yet. I'm asking about what could cause that to happen. Oh, tectonics, my friends. It always comes down to tectonics. Yes, pressure, stress, force, generally caused by tectonics, can take flat layers of rock and bend them in many different ways. Okay? This is an aspect of metamorphism. Metamorphism is any transformation in a solid. Can you think of an example of metamorphism that you probably learned about when you were a little kid? Maybe under a different term, metamorphosis?
Like butterflies?
Butterflies. A caterpillar goes through metamorphosis and completely changes its body to become a butterfly. Same concept, different material. Transformation in a solid. Now, this transformation in a solid requires that you have a parent rock, so something to start with, and it undergoes some changes. These changes include texture, minerals, and chemistry. It doesn't change states. It has to remain a solid. If it melts, what does it become?
A liquid.
Which is called magma. Yes. No longer a rock, therefore this is not metamorphism. Metamorphism requires it to remain a solid. So we're talking about a change in conditions such that our solid changes at fundamental levels without ever melting. And there can be a wide range of how intense this metamorphism occurs. We can have metamorphic rocks that are so subtly, so barely metamorphosed that we would have no idea just by looking at it that they were metamorphosed unless we looked at it through a microscope. Be like, oh yeah, I see there's a little bit of a parallel alignment here going on, right? There are rocks that are so completely metamorphosed that we have absolutely no idea what their original rock was. It really depends on the conditions. And what are those conditions? You're going to find out today. Okay? But what are the conditions that lead to metamorphism? Any guesses?
What?
Huh?
Deposition.
Deposition has to occur before a metamorphism because you get deposition of sediments and then diagenesis of those sediments, including lithification into rock, and then you get metamorphosed sedimentary rock. But remember, you can also metamorphose igneous rock. Remember how every now and then we can skip steps in our rock cycle when it makes sense? One of those skipping steps is you can metamorphose igneous rock without it having been weathered and eroded and becoming sedimentary rock, right? But for sedimentary rock, diagenesis and all that must have occurred first because diagenesis happens before metamorphism. Okay. So what are some of the common factors that we've talked about in almost every lecture that cause changes in Earth systems? So true, but I'm talking more in general terminology here, not just geological. What are changes that occur in an environment that continue to cause changes to the things that we've learned about so far? Some factors that can be changed, environmental factors.
Temperature?
Ah, heat! Bingo! How much heat do you have in your system? What does heat do again? What does it do at the molecular level?
It makes all the atoms better.
It breaks it down.
Because, like Autumn was saying, it makes your atoms vibrate faster. What is heat? It's a form of energy. You are imparting more energy to your atoms. Your atoms vibrate faster, and the faster they vibrate, the harder it is for them to maintain those bonds with each other. And when you add enough heat, melting, aka atoms break apart, bonds break apart. But when you add just enough heat, it turns out, they don't break apart. They're just more willing to move, to shift, to say, yeah, you come over here, or I'm going to go over there. And so we see changes in our mineral while it remains a solid, but without receiving enough heat for it to melt. How many of you have ever left a chocolate bar, like a Hershey's chocolate bar, out in the sun too long, realized, oh man, it got a little melty, and then put it in the freezer? I prefer my chocolate frozen. I like it when it's really crunchy, right? But if you let it melt first and then you put it in the freezer, what happens? You open it up and you find that there's some darker chocolate and then a layer of lighter chocolate. You're seeing a separation of the chocolate and the cocoa butter that was in that chocolate, that was mixed in with it before. The lighter layer, that's that cocoa butter. It has separated. Your chocolate bar may have completely melted, but let's assume it just got mushy here. It still remained what we would call a solid, okay? But there was a separation of the materials inside of it. Think of that as an example of this process, okay? Some things that can occur as a result of adding this energy. You get those that energy, that vibration, recrystallization. So commonly we will see smaller minerals recrystallize into larger ones, especially if your metamorphism is more intense. Okay? Then we'll see new minerals forming. For example, a shale made out of clays, you'll often, as a result of metamorphism, see micas forming from what those clays were made out of. We'll talk about that more in a bit. It's just an example, okay? But these are common side effects of the application of that heat. Now, where does this heat come from? Any ideas where we could get heat that would cause metamorphism? Okay, the presence of magma. Absolutely. The presence of magma can provide heat to the rock around it, locally metamorphosing. Metamorphosis. Why is my brain having... I promise I'm not having a stroke right now. Metamorphosing. Why does that sound wrong? You know when you say a word so many times that it sounds wrong? It does that thing to the rock around it, okay? To the rock around it in a zone, okay? We call that contact metamorphism, okay? Any other ideas?
The sun.
The sun doesn't provide enough energy for this to happen. I'll talk about the amount of temperature required here in a minute. Proximity to the Earth's core. Possibly. Absolutely. It's difficult for us to tell that deep down, but very possible. But definitely, the deeper you go, right? The deeper you go, the hotter it gets. We've already talked about this. Do you remember what that's called? It's a two-word phrase. Both words start with G. Gravitational gaslighting. That's it. Thank you. No, it's not. Impressive whipping out those words, though. Anyone over here remember? If I gave you the first word, do you think you'd remember?
Yes.
You want to try? All right. Just for these four, geothermal. Second word starts with the G. It's the rate at which heat increases the deeper you go underground. It's okay for you to check your notes. I strongly encourage you to. Y'all, the rest of y'all can check your notes. I might open up to the class in a minute. I'll give these four about 20 seconds to look through their notes and try and find it. It was in lecture 3. We talked about that. Geothermal is the first word. And the second word starts with a G as well. It is the rate at which heat increases the deeper you go underground. See, this is a good indicator, by the way. If I bring something up over and over, and it's not something in your notes, this isn't something to be embarrassed about. This is a good learning experience. This is something to put in your notes and make your notes better. I'm just going to... Any of y'all want to take a crack at it? No? You don't think so? Huh? No? No? Good. Yes, there it is! The geothermal gradient. Thank you. Okay, put that in your notes if it's not there already. It's pretty important. I talked about it for a while a few weeks ago, and I'm bringing it up again now. Probably worth remembering. Okay? Geothermal gradient, the rate at which heat increases the deeper you go underground, which, like Jackson was saying, the further you go underground, the more heat you get. That's exactly what that is. Okay? This occurs through burial, most commonly. Subduction of one plate under another, or layer upon layer upon layer upon layer upon layer upon layer, pushing the deeper, older layers further down. Okay? So let's talk about these heat sources. Good. Geothermal gradient. Excellent. Subduction. Burial. Rising magma, that contact metamorphism we just talked about, where magma metamorphoses the rock around it through heat transfer. Okay? Good. Now, the rate at which heat increases as you go underground through the crust, which is all that really matters to you and I practically, is about 25 degrees Celsius per kilometer of depth. I will be very impressed if any of you wrote down the range of temperature within which diagenesis occurs. Did any of you write that down from our last lecture? I gave you a temperature range within which diagenesis occurs. Did anyone write that down? Hardly anyone ever does. That's okay. It is between 150 degrees Celsius and 200 degrees Celsius. That's the range of temperature within which diagenic changes occur. After that is metamorphism. So metamorphism starts at 200 degrees Celsius. Based on this rate at which I say the heat increases the deeper you go underground, at what depth will I reach 200 degrees Celsius? Oh, mean old Professor Hart's making us do math. Yes, 200 degrees Celsius at a rate of 25 degrees Celsius. Huh? 8 kilometers! Good math skills. There we go. At 8 kilometers of depth, gaining 25 degrees of temperature for every kilometer. You reach 200 degrees Celsius. Boom, bada boom, you have reached metamorphic conditions. Okay? So at about 8 kilometers, yeah, you would start seeing metamorphic changes. Now, some other things that can influence the temperature at which these changes occur. Fluids. We've already learned that the application of water can lower melting points, right? Well, also turns out, if you add water to a really hot rock, that water can more easily dissolve things out of it. I'll show you some examples here in a little bit of a particular type of condition at the bottom of the ocean where you'll commonly see rock that has had minerals or elements stolen from it while it was under metamorphic conditions by water there at the bottom of the ocean. Okay? It's easier to steal metals and stuff out of really hot rock as that water is flowing through it. Okay? And then there's also the type of parent rock you've got. All minerals have different melting points. We've already learned this. You're old hands at that. Which means that some minerals are going to be more susceptible to change at earlier temperatures than others. Okay, so those are some factors to consider when temperature is at play. So we've talked about heat and changes in temperature being an influence for metamorphism. What is the other big environmental factor that could control metamorphism? It's also been important in past lectures and processes. Heat usually goes hand in hand with
Pressure.
You're on a roll. Yes, it's pressure. There are two types of pressure as it relates to metamorphism. Okay? There's confining pressure and differential stress. Now, to understand confining pressure, I want everyone to close their eyes. Okay, close your eyes. Stop moving, just breathe calmly. Feel your skin around you. Just kind of sit here and it feels good. Oh, good. He likes his skincare routine. All right, can you feel the pressure of the air on your skin? Is it uncomfortable? Do you notice it? I'm assuming that's a no from everyone. Good, you shouldn't feel it. Okay? You're used to it. You spent, I don't know, how old is the youngest person here? 16? Is there anyone younger than 16? Are there any 15-year-olds? Sometimes I get a 15-year-old. Okay, and everyone here in this room from 16 to 31, I assume I'm the oldest one in the room, okay? 16 to 31, we've spent that many years in this atmospheric pressure. We are used to it. The moment you were born, it probably felt a little uncomfortable because it's not the environment that you were used to for the previous 9 months of your existence, right? But after that, you pretty much got used to it. It's old hat. You're old hat with this air temperature now, or pressure now. What if you are doing the same exercise at the bottom of a 12-foot pool, 12-foot deep pool? You're at the bottom, you're 12 feet underwater, you close your eyes. Can you feel that water pressure around you now? Yeah, why? True. Now, is it more strong on any one part of your body than any other?
Yeah, your head.
Really? Why is it stronger on your head?
Because it, like, your brain, something.
It's not. No, at that depth, it's equal pressure on all surfaces of your body. Equal pressure from all directions on any one given point in space, that is called confining pressure. Okay? Equal stress from all directions on any one point in space, and that includes any one point in a body of rock as well. So when I have sediment, and it's become sedimentary rock, for example, that has been buried to 8 kilometers of depth, right? So heat is a factor here. But also pressure. Think about how intense that pressure is at 8 kilometers underground. It's a lot of pressure, right? But that pressure is coming in from all directions equally. That's confining pressure. The other one is differential stress. For me to explain this one, I need an assistant. Who would be willing to? You helped me with the last one. I think you helped me with M&Ms. Anyone else feel? Didn't you help with M&Ms? Are you sure? All right, come on up.
Of course.
Good boy. Jackson, don't you still own the
All right, go ahead and take the other side of those.
Go ahead.
Okay, let's go walk out to the middle of the room. We're going to flatten these out. Okay. Try and get them, yeah, even with each other, and then pull them tight. There we go. Perfect. Do you guys see these 3 layers of rock? This is definitely rock. This is clearly rock, right? You following me? Rock. Okay. Here, pull it a little tighter. There we go. They are flat. Originally horizontal. Just like they were deposited in. Just like they were turned into rock in. Okay? What happens if we apply stress unequally? That is, from one or more directions, stronger than in any other direction. If I take one step forward, applying stress from my direction, what do my layers of rock do? They deform. Now, if we both take a step towards each other, aka 2 forces of unequal stress, there's even more of that, isn't there? This is differential stress. Unequal stress from one or more directions. And what did it do to our layers of rock, by the way? It bent it. It folded it. Does this remind you of anything? Does it remind you of anything we looked at earlier today? That first picture I showed you, huh? Yeah. What do you think happened to those layers of rock? Thanks, man. What do you think happened to those layers of rock in that first picture?
Differential stress.
Yeah, they were subjected to differential stress, which caused them to bend, or the actual term for this, fold. Differential stress, aka unequal stress, causes physical changes in the orientation of your rock. And, as it turns out, the orientation of the minerals in your rock. The reorientation or change in the alignment of minerals in your rock is called foliation. We'll come back to that in just a minute. What direction did the rocks, did those layers of rock reorient themselves into relative to the stress applied? The stress being applied was along this plane, but what direction did the rocks go? Down. Which is what direction relative to this? Which we call mathematically and geometrically?
Perpendicular.
Perpendicular, right? The stresses were going this way. The reorientation was that way, perpendicular to the stress applied. When you have differential stress, your minerals and rocks will reorient perpendicular to the stress applied. Cough, cough, may be important for later. Write it down. Right? I'm subtle. I'm told that I'm a very subtle person. All right. Now, let's look at some examples of how this can happen, how differential stress can cause reorientation of minerals and layers. Someone tell me what you see in this close-up view of these minerals. A bunch of little rocks, well observed. What about them? They're what? There's a little bit of waviness there, okay, but what else?
Are they compacted?
Why do you say they're compacted?
I was asking.
Oh, you were asking. Sorry, I didn't hear the question mark. What else? Huh? Sediment? Is that a question or an answer? I heard a question mark on the end of that one.
That's the answer.
That's an answer? Okay, sure. We're looking. Let's say that is sediment. Sure. What else do you see about it? Is there an obvious pattern here? I haven't heard anything from this table. Emily, do you see an obvious pattern to these grains here? What are they all doing? If it seems really obvious, it's probably the right answer. Take a stab at it. Gut instinct. First answer, go. It's what? Okay, sure. They're all taking on the same shape, which is what? Oval. Yes. And oriented what way? Are they lengthwise this way or that way? Are they all lengthwise the same direction? Yeah. What has she observed? All of the grains in this have lengthened out in the same direction. How does this happen? Pressure, stronger in one direction than any of the others, right? And by the way, can I tell by looking at this what direction the pressure came from? How do I know?
Because they're flat.
They're flat this way, which means the pressure came from, yeah, top and bottom relative to this picture. How do I know that? Because they reoriented perpendicular to the stress applied. If they stretched out that way, the stress came that way. Think about a ball of Play-Doh. Let's assume that my ball of Play-Doh is like a grain of sand or any other mineral. If I apply stress like this, how is it going to squish? Out flat. Minerals do the same thing under metamorphic conditions. Okay? Now let's look at a larger view. Instead of looking at the grains, let's look at the layers. Okay? Look at those. Do you see those layers? Gosh, look at these. They're doing some funky thing like this. What is that?
They got compacted from all directions.
That's confining pressure. When it's compacted from all directions, it's confining pressure, which does not cause a deformation like this. What would cause all of these deformations? What kind of stress? Differential stress. Good. But because we're seeing this, and then overall this itself is one big fold, what does that tell me? I am seeing multiple phases of differential stress being applied. One that initially caused this layer to get deformed into these little waves, and then a larger, probably wider scale regional application of differential stress that caused this entire layer to also become folded, including all of those smaller folds in it. It gets pretty complicated, I'm not going to lie. Trying to untangle things like that, yeah.
Would you say it's like a tree? You know how like
It does look dendritic, doesn't it? Isn't that interesting? Oh my goodness, I could talk your ears off about how often dendritic patterns show up in nature. We see it in the universe out in the cosmos. We see it in the neurons in our brain, the leaves on trees, the veins in the leaves on trees. We see it in mathematical equations. Dendritic patterns are everywhere. It's a fascinating thing. But yeah, you're right. This is also another application of how dendritic patterns can show up in nature. Okay? Okay, so this can get pretty complicated to untangle, but given enough time and other relevant information, we can untangle this and figure out exactly what sort of tectonic events led to that level of deformation. Let's look at one more example. Here we have 1, 2, 3, 4 distinct layers of shale. And we can clearly see there's a white line on top of them, and I'm putting a black line on top of the white line. Those are the distinct bedding planes of the original shale. Okay? 4 layers of shale bedded on top of each other like that. And yet, when we look at this, it is clearly breaking like that. You see those breakage lines there? Normally, shale will break along layers parallel to the bedding planes. What's happened here? Clay is a mineral that is flat. When you get shale deposits, or when you get clays deposited on top of clays, they are often randomly oriented. When shale is deposited, they're deposited flat like this, which is why they are often water resistant. Water cannot flow through the layers of shale very easily because it's very flat, water resistant minerals on top of each other, like the pages of a book. How easy is it for you to pour water through a closed book? You can't, at least not without super saturating it. Same thing here. But what happens if I apply differential stress to those minerals? What's going to happen to them? They're going to reorient. In what direction? Perpendicular to what? Hold on to that thought. Perpendicular to what? Someone over here. When differential stress is applied, the minerals reorient in what direction? Perpendicular to? Perpendicular to the applied stress. Bingo! So if I were to say have layers of shale like this and apply stress from that direction, yeah, my shale, or I should say my clays in my shale, are going to reorient perpendicular to that stress. And now my shales will break off along those planes. So I have the original bedding planes still there, but all of my clays have reoriented in a different direction based on the stress that was applied to them. Are you following this concept? Are you picking up what I'm putting down? You smelling what I stepped in? All right, good. Oh man, Tuesdays. Two astronomers spent 24 hours studying the moon, then they got tired, so they decided to call it a day. Eh? Yeah? No? No? I know it's dumb. Hey, who's my ba-dum-tsh guy? All right, there we go. Okay. So now let's talk about stuff relevant to your Metamorphic Rocks lab. Okay, because yes, you are getting your fourth lab today. It's being assigned today. All right? So, metamorphic textures are the first thing you need to worry about when it comes to identifying metamorphic rocks. Metamorphic textures are a description of the alignment and size of crystals or minerals, grains, whatever the case may be, in your metamorphic rocks, okay? So you've got foliated, which I do need to let you know, some literature calls foliation rock cleavage. I don't like that term because mineral cleavage is something I've already taught you about. So I don't like that term being applied to something else totally different. So I only call it foliation, but just know if you do your own research online to help you with the material, you may see some sources call it rock cleavage. I just don't like that, okay? So I call it foliation. You have different degrees of foliation. You've got slaty foliation, which is very light, very straight layers, very subtle metamorphism. Then you've got schistose foliation, which is more moderate foliation. And then you've got gneissic foliation. I'll go over all of these. I'll show you examples of all of those here in a little bit. Okay? Then we have non-foliated rocks, the ones where our minerals have not been oriented perpendicular to any stress. What type of pressure do you suppose causes non-foliated rocks?
Confining?
Huh?
Confining?
Confining pressure. Yes, if differential stress causes foliation, confining pressure is where we will find non-foliated rocks. Okay? Then there's a third type, porphyroblastic. Porphyroblastic metamorphic rocks have large crystals that have grown in them after the process or during the process of metamorphism. Are we all right over here? What's going on? Okay. Okay, so porphyroblastic rocks. Let me show you an example here, actually. Where? There it is. Porphyroblastic rocks. Like this, where you have a metamorphic rock, and a much larger crystal has grown inside of it. Much larger relative to the rest of the rock around it. This is a garnet, by the way, that has grown inside of this mica schist, which is a metamorphic rock. Okay, can you all see that garnet? Yeah? Very cool. I'll pass that around, actually. Porphyroblastic. All right, let's start talking about foliation. There are several different types, or not different types, I should say, different manners in which foliation can occur. Okay? Foliation itself is the parallel alignment of minerals within a metamorphic rock. Parallel alignment of minerals. There are a couple of ways this can happen. Flattening. If I apply stress and pressure, just like with that Play-Doh I talked about, my minerals will squish out, and I'll get flattening of all the minerals. There's recrystallization, where if my mineral is hot enough and under enough pressure, aka the environment is ideal for this sort of thing, my minerals, while not melting, could simply recrystallize themselves in a new orientation. Recrystallize in a new orientation perpendicular to the stress being applied. Then there is reorientation, okay? Which is when my mineral literally goes like that inside of my rock. All the minerals just do this. They reorient. Again, perpendicular to the stress applied. So there's the squish, the recrystallization, and the reorientation. Okay? Those are the three ways that you can get foliation inside of a rock with the application of differential stress. So while this is happening, as our minerals are reorienting, recrystallizing, or flattening relative to the differential stress, our layers of rock are also responding to that differential stress. And how are they responding? How did our layers of rock respond to the stress? Yeah, they folded. So we will usually find folds in the rock and foliation in the minerals after differential stress has been applied. Okay? So let's talk about the different types of foliation. Slaty foliation. Yeah.
So how does it not just break? Rock. You said it was fully formed like thick rock.
Yeah, it's solid rock.
Break.
Why does it not break under all that stress? Great question. It can, unless it's under the right heat. Think of it this way. Let's go back to that chocolate bar. Who doesn't love using chocolate bars as an example at 10 o'clock in the morning, right? It definitely doesn't make us hungry at all. Okay, so here I've got my Hershey's chocolate bar. I pulled it straight out of the freezer. If I start putting stress on it, what's it going to do? It's going to snap. I don't care, I'll still eat it, right? What if it's at room temperature and I start to bend it? It'll bend for a second, and then eventually I will reach a point where it breaks, right? What if I heat it up just a little bit, maybe 3 or 4 degrees above room temperature, and I start to bend it? It's going to keep on bending. It's really flexible at this point. So, the temperature of my material is a huge factor in how flexible it's going to be, or how rigid it's going to be. This is going to be a factor that comes up, by the way, in a couple more lectures when we talk about earthquakes and when we talk about things like landslides and we talk about all of the ways that different materials respond to different forces. Temperature and pressure are huge factors. Okay, great question. Any other great questions? Okay, well then let's talk about slaty foliation. This is the foliation you get from the least metamorphosed differential stress applied metamorphic rocks. You get slate. This is slaty foliation that you see in the metamorphic rock slate. I'll pass this around in a second, but you'll see that all of the layers of clay, by the way, this is what you get when you metamorphose shale, okay? All the layers are parallel aligned with each other, and you can see this really flat plane along which this rock breaks. That is slaty foliation. Very flat layers, okay? We use slate for flooring materials. It's been used for centuries. Actually, I'm going to go ahead and say millennia probably at this point, as a roofing material for protection against rain and stuff. You would just take pieces like this and stack them on top of your huts for roofing tiles, okay? So you're looking at slaty foliation in the rock slate right there, okay? Very flat layers. Then we get more medium intensity metamorphism. You'll usually get some sort of schistose foliation. This is the rock schist. And yes, all the different types of foliation are named after the types of rock we typically find them in. So schistose foliation, found in schist. Okay? S-C-H-I-S-T. Schist. Okay? Now, this is not quite as flat as that slaty foliation. It has some more undulation to its layers there. Something you'll notice about the rock, we'll go over these rocks here in a minute, is that it's also made out of larger crystals, okay? Metamorphism has gone on even longer. If I took that slate and metamorphosed it again for longer and hotter and a little bit more pressure, I'd get this schist with this wavy, sort of undulating schistose foliation pattern to it. Then we've got gneissic foliation, also called banding. Why? Because when you get really intense metamorphism, you tend to leave behind the just flattened, reoriented, and recrystallized sort of effect, and you tend to stick with the squished effect. Okay? Basically what you're looking at here, in every single stripe of white and black in this rock are squished, stretched minerals. Okay? Huh?
They use that for countertops.
Yeah, gneiss is one of these rocks that is commonly confused with granite. How can I tell the difference between a granite and a gneiss?
Granite is more spread out.
What in granite?
Like,
I think I know what you're trying to say. Just reword it.
like the minerals, they're all not all like squished together. They're more.
They're in the shapes they grew into. Exactly. You can tell gneiss from granite by looking at the minerals and seeing my minerals are in the shapes they grew into versus squished, stretched, long, thin bands of color. Okay? Now, there's nothing really wrong with using gneiss as a building material. It's really strong rock, especially if it's got quartz in it, which a lot of it does, depending on its source and, what the parent rock was. But marketing it as granite is obviously dishonest, right? So now you know the difference. Yeah, don't get scammed, y'all. Don't get scammed. Pass that one around too. And again, like I said, I will be talking about each one of these types of rock here in a minute. First, let's talk about the other textures. You've got of course, yes. You've got non-foliated metamorphic rocks. Non-foliated ones have no Onik. Non-foliated rocks have no non-foliated rocks have no right, but what do you call those? Foliation. Non-foliated rocks have no foliation. It was a dumber question than you were probably thinking it was. I was just checking to make sure everyone was awake. Okay? Non-foliated rocks have no foliation. That means no parallel alignment of minerals. They are simply recrystallized, slightly chemically different versions of their parent rock. Okay? So they are going to be different, but there won't be any of that parallel alignment effect. Okay? For example, limestone becomes marble. Yes, if you've probably heard of marble before. You've been playing with limestone for a week now, right? Marble is simply metamorphosed limestone, which is why sometimes we see what look like fossil patterns in marble. Just remember, after metamorphism, the fossil is gone. Sometimes we can see a relic pattern of a fossil, but the fossil itself is long gone. Okay? Then we've got that porphyroblastic, which I already handed around, right? This one right here, where it had the garnet in there. But you can find starlites, andalusites, any number of other minerals in these porphyroblastic rocks. I kind of think of these things, the garnets and starlights and whatnot, in porphyritic rocks. They're kind of the trash cans. Everything else that's left over kind of gets thrown into another mineral, and that becomes this. Okay? There are lots of different varieties of garnets, and that's because they're kind of made out of the leftovers, for lack of a better term. Okay? Okay, so those are your three textures: foliated, non-foliated, porphyroblastic. So how do we go about identifying these metamorphic rocks? Well, you need to identify the texture: foliated, non-foliated, porphyroblastic. Then you need to figure out how large are my grains. Then you need to figure out, if you can, things like composition. Then you need to figure out what it is. Okay, those are kind of your biggest tools here. Is it foliated? Does it have any layers? What's it made out of? Is it knocking back?
No, it sounds different in different spots.
All right, sure. Yeah. I was just waiting for... Right?
It just sounds different in different spots.
The gremlin in my rock didn't knock back at you. So let's talk about some of the common examples of metamorphic rocks. I already handed around slate. I won't hand it around again, but I'll show you guys. Slate, this one right here. Slate is made from metamorphosed shale or other mudstones. Under differential stress, it is made from very, very small grains. Mostly still clays that have simply been foliated, reoriented perpendicular to stress. Okay? They are just starting to change chemically. What are they going to change into? Well, they're going to change into micas. We'll get there in a second. But just like with the original shale, they get their colors depending on what else is in there besides just clays. Green slates usually mean that there's still some chloride in there. Red means that there's some iron. Black means there's some organic carbon. So on and so forth. Okay? This schist, well, actually, there's another transition. Let me move on slides. Phyllite, which is this one. Phyllite is the transition between slate and schist. It's just those foliation layers are just barely starting to take on that sort of undulating, wavy shape. Okay? Not as much as we see in schist, but definitely more than we saw in the slate. And you can tell, just by how glossy and shiny this is, my minerals are getting larger too. They're starting to transition to those micas from clays. Okay? Yeah. Oh, I thought you were putting your hand up. There you go. Then after phyllite, that's where you get schist. This is your moderate, mid-grade metamorphism. Okay, so crystals, definitely large. We can easily see the crystals in here. As a matter of fact, I can see little garnets in here too. Right? I'll pass this around again, but there are tiny little garnets that you can see in there. Those little black dots that you see in the texture. You can clearly see the foliation still. It's just wavy. Schistose foliation in a schist rock. Now, the tricky thing with schist is there are so many varieties of schist that we don't give them unique names. We literally name schists exactly after what they're made out of. That's just the easiest system to have when you have so much variety. For example, I would call this one a muscovite mica garnet schist. Why? Because it's mostly made out of that silvery muscovite mica that we learned about in Lab 1, and it's got little garnets in it. There's no fancy name for this because we just call it by what it's named after, by what it's made of. Okay? Which actually makes it simpler, right? Pass that around again so you can look for the little garnets now that you know they're there. Now, if I take that schist and I metamorphose it even more, even harder, even longer, that's when it becomes that gneiss. Gneiss spelled G-N-E-I-S-S. Where is, there it is. Okay, now, I can get this gneiss by metamorphosing that shale into slate, and that slate into phyllite, and that phyllite into schist, and that schist into gneiss. But there are other types of rock that can become reoriented and metamorphosed into gneiss. This gneiss that I'm holding in my hand is made from sodium feldspar and amphibole. Do you remember any other rocks we've learned about that are made from sodium feldspar and amphibole? Or calcium feldspar and amphibole? No. Diorite. Look at those two. They're made out of the same stuff. What's the difference? Lines and one has dots. What was that? The amount of quartz? I mean, both might have small amounts of quartz, but that's impossible for us to tell without doing an actual chemical analysis. Good thought. What do you mean by lines and dots, Chris? Be more specific. Be a little more scientific.
That one has speckles. That one has lines.
Right. Be a little more scientific. What are the lines and what are the speckles? What do we call this pattern? Huh? It's made by differential stress. I'll get to you in a second. Okay.
I was going to say one was squished down and one just had minerals.
Right, but what do we call that?
Oh,
Foliation. This one is foliated and this one is not. The minerals in this just grew there. The minerals in here were foliated. If I took this diorite and I subjected it to the right metamorphic conditions, I would get this gneiss. Okay? Same exact minerals, different pattern. Easy to tell which one's igneous and which one's metamorphic. But remember to use that scientific terminology. Okay? It's real important. Even if you're not going into geology, as long as you're in my class, remember to use that right terminology. Okay? So, I'm going to pass these both around again so you can see that side-by-side comparison. Now let's talk about some of the more common non-foliated metamorphic rocks. Marble. Marble comes from metamorphosed limestone, which means it's made out of? What's limestone made out of? It's a kind of rock made from a mineral which we call
Stone, no, not stone.
Oh, balls. Could be
no.
marble.
Wait,
You had a 1 in 26 chance there. That was a good shot. Limestone is made calcite. Limestone is made from the mineral calcite. That's it reacts to acid, right? Limestone is made from calcite, and since marble is made from limestone, marble is then made out of calcite. Yes, I'll pass this around. You can drop acid on this and it will fizz. Why? Because it's made out of calcite. We're looking at, now he's smelling it.
that's really bad.
He's knocking it again. All right. You're going to see large crystals of calcite in here. Okay, whatever the limestone was made of before, it's been recrystallized into larger grains of calcite and made this marble. Now this marble that I'm holding is kind of a nice pleasant peach color. There might have been a little iron or maybe a little potassium feldspar in there in that limestone that got trapped in there. You have all sorts of different colors of limestone. There's whites, browns, yellows, purples, blues. Okay, I've seen all sorts of different types of marble, and the coloration comes from whatever else was in that limestone. Okay, when it was metamorphosed. Marble, also a very common building material, but why is it a bad idea to build something you want to be durable or long-lasting out of marble?
Doesn't it break easily?
What's the Mohs hardness scale of calcite? It's a 3, y'all. Okay? Calcite, very soft. Also, what do we know calcite breaks down in the presence of?
Water?
Water with what?
Actually, salt inside of it, right?
Mm-mm.
That H2O.
There's something in the atmosphere that gets dissolved in the water.
Carbon dioxide.
Carbon dioxide, which makes what? When you dissolve carbon dioxide in water, what does it make? Yes, that's stuff, but what is it?
I forgot the acid's made, but
It's a type of acid made from carbon dioxide.
is it the acid that we use in our lab?
No, that's hydrochloric acid. Carbonic acid. Carbon dioxide dissolved in water makes carbonic acid, okay? Bless you, okay? So carbonic acid will dissolve marble very easily, which means that it's not a great choice for building stuff with. Wouldn't make gravestones out of it, wouldn't make countertops out of it. It's softer than the butter knives that you drop on your countertop, right? What a bad day that would be. You're making a sandwich, you're buttering your toast, oh, it slips, ooh, tonk, big chip out of your countertop. Ah, you built with marble, you fool! Okay? Not harder than steel. Steel is a hardness of 6 on the Mohs hardness scale, and marble is a hardness of 3 because it's made out of calcite. Okay? Okay. Quartzite. Quartzite is the non-foliated metamorphic rock we get when we metamorphose quartz sandstone. So just like with that marble, our grains have gotten fused together. Except instead of calcite, we're talking about quartz, which means you scratch glass with this, it's going to scratch. You try and scratch steel with this, you're going to scratch that steel. Don't scratch a pocket knife if you care about it, right? This is quartz. It is grains of quartz sand that have gotten fused together through metamorphism. Okay? Where does the coloration come from, do you think? Yeah, whatever was in that sandstone before. A purple quartzite like this probably comes from a red sandstone that had iron in it, right? But again, you can have so many different varieties of quartzite. All right? Quartzite. All right. Contact metamorphism. Contact metamorphism is what happens when you get that rising body of magma approaching the surface, starting to move through the crust. As that happens, what does it do to the rock around it?
Heats it up.
Huh?
Heats it up.
It heats it up. Exactly. We talked about this before when we learned about igneous intrusions. That magma is not going up through the surface and saying, "Excuse me, would you mind making way for me?" No. It's melting rock as it moves upward, incorporating the melted rock into itself, changing its own composition. But what else is it doing to the rock around it? It is heating up an area of the rock around itself, which is going to do what to that rock? What's been the whole subject of today? It's going to metamorphose that rock around it. There's going to be a zone of metamorphism around our magma chamber. Okay? Now, is there any differential stress here? What do you think? I hear a yes. I hear a no. Anyone want to say yes? Anyone want to advocate for yes? Do we all agree with no? So many abstentions. Y'all would fail as a jury. Okay? There is no differential stress here. There's nothing tectonically happening to cause differences in pressure. Okay? So we have confining pressure and the presence of heat by the proximity of this magma chamber. So here we have shale, limestone, quartz sandstone, and more shale. Okay? When shale is metamorphosed under confining stress and sufficient heat, it makes a type of rock called hornfels. Remember, if this were differential stress, it would make slate because all those clays are getting foliated. But there's no differential stress. There is confining pressure plus the heat, which means that we get, it was hiding right there, hornfels. Okay? I'm going to pass this around. You'll notice that there is no layering. There is no foliation of any kind. But it's still clay. This is essentially just a baked cook brick. It's essentially a brick. You just cook mud, more or less is what it comes down to. There's no foliation, so it more or less looks like a brick. That's called hornfels. Limestone will metamorphose into what?
Quartz.
There's no quartz in limestone.
Not quartz, marble.
Marble. Bingo. Quartz sandstone will become quartzite. And shale becomes hornfels. So we get this zone of metamorphic rock around magma chambers that are the non-foliated metamorphic rocks of the parent rock that was there before the magma chamber showed up. We call this a metamorphic areole. Okay? Here's a picture of one. This is in New Zealand, I believe. Here is the actual igneous pluton. This is diorite. Okay, this pale rock down here is diorite. Okay, and what's above it? This metamorphic areole, this zone of altered rock. Okay? I mean, you can see the transition from one to the other right there in this mountain. I mentioned that water plays a pretty big role in how you can change hot rock chemically. Well, where we've got our divergent plate boundaries, where our plates are separating away from each other deep in the earth, okay? We've got a whole bunch of water that's seeping down through cracks into that zone. The super hot water interacts with the super hot, cooling off, metamorphosing rock down there and removes metals. Those metals get dissolved out of the rock by the water, leaving behind hydrothermally metamorphosed rocks. We get things like talc schists and all sorts of other weird, random metamorphic rocks down there. And where do those metals go? Where does hot water like to go? Where does hot anything like to go? Up! Yeah, it's less dense, and therefore it wants to go up to zones of less pressure. And so we get these things at the bottom of the ocean called black smokers. Okay? It looks like a chimney that's spewing smoke out into the bottom of the ocean. Any of you ever watched a National Geographic or Animal Planet documentary or Discovery Channel documentary about the bottom of the ocean? Pretty much every single one of those shows a black smoker at some point, okay? It just looks like smoke spewing up out of the bottom of the ocean, but it's not smoke. What you're looking at is boiling hot water filled with dissolved metals that's reaching the freezing cold water at the bottom of the ocean. What happens when something really hot meets something really cold? Anything that is dissolved in that hot water instantly precipitates. You're looking at microscopic particles of metal that have been dissolved from deep underground and brought up to the surface by that hot water. And it's instantly precipitating in that cold water and drifting down and falling into the bottom of the ocean. Imagine, after billions of years, how much metal is just sitting on the bottom of the ocean. Why don't we go to get it? Why don't we mine that? Why don't we stop strip mining our planet and just scrape all that mineral dust off the bottom of the ocean?
Feel like pressure can't even go down there.
Oh, the conditions, sure, yeah, you betcha, right? Huh? Oh no, that wasn't Scottish, bro. That was more like Michigan, Wisconsin, yeah. Oh, you betcha. Okay, I could go Scottish if you want, though. Why don't we? Well, sure, the conditions aren't habitable. It's not ideal. The amount of technology it would take to go to the bottom of the ocean and get all that metal, and then how are you going to bring all that heavy metal up to the surface? The amount of energy it would take would be monumental. Possible. But is there any other reason why we don't do that? Or shouldn't do it? Maybe we think about it morally. Other than the technological issues.
Mister, you know those big old balloon things that they put underwater and they're filled with air to bring stuff up?
Yeah.
Didn't they do that?
If you had a tank full of helium and you just carry it around with you on your back, and then you put all that helium into a balloon, would it lift you up? No, you're still carrying the tank. You're still carrying the same amount of helium that you had before, right? There's a lot of physics that you have to overcome for this to work. It's like if you stood in a bucket, could you pick yourself up? No, but you're strong enough to pick up the bucket. Why can't you pick it up? Your mass is part of the equation. So is the mass of the canister. So is the helium is always there, right? You have to provide enough physics to overcome mass, or enough buoyancy, I should say, to overcome mass. It doesn't work without the right equipment. Your idea of taking gases down there, sure, there may be some value to that, but you have to leave something behind. You'd have to leave behind enough mass at the bottom of the ocean to lift some certain amount of mass back up. And what good does that do if the whole point is bringing up tons of metal? You know? So there's a lot that goes into this. What I'm trying to get at, though, is what about the ecosystem down there? These black smokers are crawling with life. Mats of bacteria, crustaceans, fish, all sorts of stuff lives down there. And right at the bottom of the food chain are chemosynthetic bacteria. Oh my goodness, friends. Chemosynthetic bacteria are astonishing. The oldest forms of life on Earth as we know it. What do I mean by chemosynthetic? Do you know what photosynthetic means?
It takes energy from the sun.
Takes energy from the sun. What do we know about that are photosynthetic?
What?
Plants. Do you know what came before plants? Bacteria. Do you know what came before photosynthetic bacteria? Chemosynthetic bacteria. Organisms that live at the bottom of the ocean have never seen and will never see the sun. These are the first forms of life that our planet ever had. Billions of years ago. Possibly 4 billion years ago. And by the way, the greatest evidence that life could exist somewhere else. If we need evidence that life could exist somewhere other than a planet like ours, that chemosynthetic bacteria is the best evidence we've got. Those mats of chemosynthetic bacteria, the sun could go out right now. We would all die in about 8 minutes. It would take 8 minutes for the last ray of light for the sun to reach Earth, and then Earth would instantly start to cool off. Stuff would die. Everything on the surface would be dead pretty quick. Right?
This whole planet could cool off in 8 minutes?
No. We would see the last rays of the sun in 8 minutes, because it takes 8 minutes for the light from the sun to reach us. The last rays of the sun, if our sun just disappeared, it would take 8 minutes before we saw the last ray of light to realize it. Okay? And then after that, there would be a cascade of effects that ultimately led to everything on Earth, everything on Earth's demise. Okay? Except the stuff living at the bottom of the ocean, this chemosynthetic bacteria that never has cared a whit that we have a sun. The entire surface of our planet could get covered in ice for 1 billion more years, and as long as that metal keeps flowing out from our ocean's crust, that life goes on. How crazy is that? Now consider that there are at least a half dozen moons in our solar system of Jupiter and Saturn that are covered in ice and have liquid water and a hot metal core. The same conditions exist on these half dozen moons that exist at the bottom of our ocean. Who's to say there's not chemosynthetic bacteria there or some other form of similar metabolizing life? All that they need is metal to strip atoms off of to sustain themselves. They do it chemically. They don't use the sun. There are 4 miles of ice between space and the liquid water on some of these moons. That's essentially a solid atmosphere protecting that liquid water from space. My friends, this is the greatest evidence that we have that there's life other places. And that evidence is right here on our own planet. Just wanted to point that out. Okay? Okay, so subduction, causing metamorphism, and burial. These are 2 ways that we can push rocks deep underground enough to reach the temperature and pressure requirements to have metamorphic conditions. Okay? Friction is a big factor that introduces both pressure and temperature. So we often see metamorphic zones at subduction plate boundaries. Okay? Typical burial, like on a continental crust, will occur, metamorphism will occur about 8 kilometers depth because that's when you reach that temperature requirement. Regional metamorphism is what we call it when there's a huge, broad area that's being metamorphosed by some tectonic event, usually the collision of tectonic plates. Big example, India running into Eurasia, making the Himalayan mountain range. Okay? The entire Himalayan mountain range is metamorphosed ocean floor, old Indian crust, and old Eurasian crust. Okay? It's mostly metamorphic rock because of how long and how intensely those 2 continents have been running into each other. A few other places that we can get metamorphic rock. Fault zones. So the cracks in the earth along which earthquakes happen because stress builds. That's stress. What's that stress doing? Partially metamorphosing the rock on either side of that crack in the ground. Okay? So we can get metamorphic rocks that occur in fault zones. And then impactites. Impactites are fascinating. When an asteroid or a meteorite hits the earth, it lands with so much force and energy, it instantly flash melts the section of crust it runs into. But what happens around that melted zone? Metamorphism. So not only can we go to an impact crater and find a whole bunch of information about the meteor and about the zone in which it landed, but we can see the effect of metamorphism around that crater as well. Okay? Impact metamorphism. This is something I already talked about. We've got your degrees of metamorphism, how intensely they're being metamorphosed based upon their proximity to the zone of metamorphism. So light metamorphism way out here, moderate metamorphism the closer you get, and then deep down in here where you're getting that super intense metamorphism, you'll get your stuff like your gneiss. The type of minerals that you find in your metamorphic rock largely have to do with the temperatures and pressures at play. Okay? So where we've got our different rock types, which are based upon our mineral ingredients here, we can see increasing metamorphism and therefore a higher temperature gradient the further we go this way. So we start off with our chlorites, our muscovites, our biotites. That's where we've got our slates and our phyllites. We move into things like garnet and starlite, and that's where we get our schists. Sillimanites, quartz, feldspar, present throughout all of that. That's where we get our gneiss. Anything higher than that, anything that's more metamorphosed than gneiss, is going to end up melting anyway, and therefore gneiss is the most metamorphic rock we can get. Now what happens when I take a gneiss and heat it up to the point where some of the minerals melt, but not all of them? Because remember, partial melting is a thing. When I take, say, a gneiss and I heat it up to the point where the feldspars and quartz inside of it melt, but not the amphiboles, I will still get foliated layers of amphibole, and between those foliated layers of amphibole, I have granite, feldspars, and quartz that have recrystallized from the magma that they melted into. This gneiss got hot enough to melt the quartz and the feldspar, but not the amphibole. And so it's still got foliated metamorphic amphibole, but igneous quartz and feldspar crystals in between. We call this a migmatite. It's a partially melted gneiss. Pretty cool. Okay, any questions? All right, well, you have a Lab 4 PowerPoint that goes over pretty much everything that I just talked about. Lab 4 is officially assigned. Go ahead and move into lab time now. I will be here to answer any questions that you've got. Yeah, you may. Yes. Yes, I will get you Lab 3 in just a minute. I'm going to go ahead and end the recording here. Please remember to come prepared next time with questions. And for my online students, please remember that you can always send me an email with your questions, and I will respond to them during the exam review recording. All right, bye.